So, good evening, everyone. Today we will continue with the UV visible spectrophotometry. In our last classes, we have discussed about the single beam spectrophotometer. Then we had discussed about the conventional split beam spectrophotometer. Okay, how it functions. So we have seen that. Then we have discussed about the image processing based spectrophotometer. How does an image processing based spectrophotometer it looks like, and how is the construction different from that of the conventional spectrophotometers, right? Then from the image processing based spectrophotometers, how we can analyze the data, that we have also discussed. And we have also discussed that the colored solutions, they act as filters, and accordingly from the wheel chart, if we see the complement pairs of the colors, how they can alter the spectrum of a given of a spectrum of a given color solution, right? Then this is the wavelength spectra of the color which we have obtained from the image processing based spectrophotometer. Then we have discussed about the different types of spectrophotometric detectors. We have discussed about the phototubes. Uh, in the initial days, phototubes was used, but nowadays it is not much used. On the contrary, we use basically the photomultiplier tube, which is an advanced version of the phototube, right? Then we also talked about the diode array and charged coupled detectors, which are used as the detector for the image processing based what you call as spectrophotometers, right? And I have also told you that apart from this, we also have CMOS devices or detectors. Okay. So these are the different types of detectors, and we have discussed about the functionalities of the thing. Then we also discussed about the sample holders. So if you see the polystyrene and the PMMA cells, they are mainly used in the visible region. Okay. And yeah, for the full UV visible length, this radiation length or the electromagnetic radiation range, we basically use the Quartz Cell, which covers the measurement wavelength range from 190 to 2500 nanometer. Okay. So today we will see how we can analyze a specific analytes, and if a given solution of analyte is given, how we can find out the concentration. Okay. Say for example, we are given with an analyte A. Okay. So we are considering that this analyte A, it is soluble in water. Okay. Why we are considering that it is soluble in water? This is because most of the analytes which are biologically active, they are soluble in water. Okay. Hence, we are considering that the analyte A, it is soluble in water. However, um, if you want to extend it to other analytes, even those which are insoluble in water, so you just have to change the solvent from water to that solvent. Okay. But so you can generalize the thing for the case of by replacing water in my lecture with solvent. Okay. So suppose we are given with an analyte A and we are told that in a specific sample we want to analyze the content of A. So what is the first step? The first step would be that we dissolve that analyte into water and we prepare a solution. Okay. Now with this solution, what we will do, we will go for UV visible absorption measurement. Okay. So how will we do the UV visible absorption measurement? We will do it on a wavelength scanning using the wavelength scanning method. Okay. So this is nothing but it is called UV visible spectrum scanning. What it is written over here. UV visible spectrum scanning. Spectrum means this it covers the frequency components. So since wavelength is associated with the frequency, we call it the spectrum scanning because the electromagnetic radiations of the different frequencies will be involved over there. So initially what happens, if you see, as we were discussing yesterday, suppose we are considering that the full wavelength scanning will be done and we are using a quartz cell. That means we have to scan in the region of 190 to 800 nanometer. Okay, because above 800 nanometer we enter into the IR region. First near IR region and then near IR region we enter over that region. But usually the UV visible spectrophotometers, they are not associated or they are not capable of measuring the NIR recordings. So we will be doing a wavelength scanning when we are using the quartz cell in the range of 190 nanometer to 800 nanometer. So in that case, what the system will do, it will initiate the absorption measurement at 180 nanometer and it will scan through up to the point of 800 nanometer. Okay. Now, when it is doing the scanning, it may change the wavelength by 1 nanometer resolution. That means after 180, there will be an increment of 1 nanometer. You can change the setting to say 2 nanometer. So depending upon what kind of scanning you want. So larger the step, the faster will be your scanning, but you will be losing the resolution of the scanning to a great extent. If you go above 1 or 2 nanometer this step size, then you will start losing the resolution. Okay. In some cases, if you want a very fast, you can go for a step of 10 nanometer, uh, the scanning step of 10 nanometers and so on. So in the case of 10 nanometer, what will it will do at 108, sorry, 190, I suppose. Yeah, it is 190. So after 190, it will go for 200 nanometer scanning. Then after 200, it would go for 210 nanometer and so on up to 800 nanometer. But what happens to the this wavelength radiations within 200 and 210? This is completely missed, right? Your scanning will be faster, but this will be missed. However, if you go for a step size of 1 nanometer, so what would happen? After 190, it will do the measurement for the 191, then it will do the measurement for the 192 and so on. So you will be getting a better resolution. But you will be it will be taking a long time. So depending upon your need, you can you can adjust the step size at what wavelength step size you want to do the measurement. Okay. So once you have done this measurement, you will get this kind of curve. You will get this kind of curve. Okay. Now, this is just a sample curve. So you will be having some wide spectra, some sharp spectra, and something like this, right? So I'm drawing another one to give you a better idea. So it starts like this, you get like this, maybe this, like this you get, okay? Now in this case, you can see there are two peaks associated with the analyte A, okay? So the measurement of the analyte can be done at these two locations, okay? At these two locations, say this is lambda 1, this is lambda 2, okay? So in general, we call it the peak where we want to do the analysis. We take the highest peak, and that highest peak, it is called lambda max. Okay. However, in this case, if you see, we have got two sharp peaks. Maybe lambda 1 is the lambda max and lambda 2 is slightly lower than the lambda 1. Okay. However, that is also you can also use it for the analysis purpose. Okay. So what happens over here? So first, once we do the spectrum scanning, fix or identify the wavelengths at which we can do the single wavelength measurement. Okay. So after the identification of this single wavelength measurement for the analyte which we have been given, so what you can do is that you can take, you have to make different concentrations, different solutions of concentration, okay, of the analyte A. Say we prepare an analyte stock solution of 100 mg per 100 ml. That means we have prepared a stock solution of 1 mg per ml. Okay, so we have got to this. Now after getting this, say it is the highest concentration, so it is say I want to make four concentration solutions of four concentration. So the first one would be the C4. Now I dilute it. Say I take the 1 ml of this one and I take the stock solution over here, and I take I know the concentration of this one, it is 1 mg per ml. Then I dilute it to 10 ml. So the concentration of the new one is 0.1 mg per ml. Okay. So accordingly, by changing this volume of the stock solution and by changing the volume of the dilution, we can obtain different concentrations from the stock solution, lower concentrations from the stock solution. Stock solution, you please keep in mind, many students they make a mistake. Stock solution is always, it will always have a high concentration, and as we dilute it, we get different concentrations. So the serial dilutions helps us in getting lower concentrations. Okay. So suppose we have got four solutions of concentration C1, C2, C3 and C4, and from the previous spectrum scanning, what I have done, I have identified the lambda max. Say for example, in this case I will go with lambda 1. So the lambda 1 is my lambda max. So I will set the spectrophotometer to work at lambda max. And now the spectrophotometer will be capable of giving me results uh, at this results means absorption values at this lambda max. Okay. Now, another important thing is that so okay, I will come it a bit later. So we got this lambda max. Now I will put the lowest concentration solution, the C1, into the slot, and I will measure C1. Then I will measure C2. Then I will measure C3 and C4. Then I have to fit a curve of y equals to mx plus c. Okay, so there will be straight line which will be passing through. Now, since there will be a straight line, it will be passing through all the points. You will be getting an equation for this, and this equation is called the model equation. Okay. However, we have while we are modeling the system, we need to take care that this c should be 0. Okay, the constant should be 0. That means this straight line, model straight line, which should pass with 0. If it does not pass with 0, it means that there will be some intercept, and that means that at concentration equal to 0, you are getting some absorption. Okay, you are getting some absorption, and we do not no, so at concentration 0, if there is some absorption, that means that even at 0 concentration there is some analyte, and hence it is absorbing the thing, absorbing the radiations. So we do not want that condition to happen. Okay, so that's why we need to uh, see that the C is always 0. Okay, and we need to put a constraint while we are doing the modeling. Okay, another important thing over here is that while you are doing so, no one of you asked, sir, what happens if the solution or the solvent, it also absorbs some radiations? And definitely yes, even though I am telling that water is transparent, it would absorb some amount of the electromagnetic radiations. There are many solvents also which has the capability to absorb a large number of samples. So for that reason, before we start to do any kind of analysis, we have to zero balance the spectrophotometer. Okay, we have to zero balance the spectrophotometer. Now, this zero balancing, it is also called baseline removal. Okay, baseline removal, because we are talking about some this what you call we are talking about this analog sensors, right? Now these analog sensors, uh, they will also have their some there will be some deviations and all these things. So these due to the solvent, whatever the absorption is happening, that you have to balance it. Okay, so for that, what you need to do, I will go back to our initially the single beam spectrophotometer first, and consequently the other spectrophotometers. In this case, if you see, there is only one slot. So in a single beam spectrophotometer, if you see, there is only one place for putting the sample, right? Now, since there is only one place, so what to do in this case? So initially what happens, we take the reference sample. Reference sample is usually the solvent. Okay. Now we take the reading of the solvent, and it is kept in the memory of the system of the software. Then what happens? Then after we have measured the difference in the first step, in the second step, we use the sample solution. And the output of the sample solution you will get, say, absorbance of the sample solution you will get by this formula, this say A sample solution intermediate INT minus the AR REF, A reference. Okay, so what you will be getting is that you have to give a you have to minus or you have to subtract the absorption values of the reference solvent to get the actual absorption of your sample. Okay. So conventional split beam spectrophotometers, over here, if you see, there are two places, one for the reference and one for the sample. And in both the places, you are measuring the absorption and you have the photodetectors for individually for each of them. And it is automatically calculating the difference or it is subtracting the baseline of your reference. Okay, so you need not to do anything in the case of conventional split beam spectrophotometer. However, for the single beam spectrophotometers, you have to do the analysis. Okay, you have to take the reference sample first and you have to store it in the memory of the software, and then whenever you will be doing the sample analysis, then it will subtract that baseline from your sample solution absorption spectra and it will give you the actual absorption spectrum or absorption values for your samples. Okay. Now, in the case of the image processing based spectrophotometers, again, if you see, there is only one this sample holder. And due to this reason, you only need to do you have to first do the reference spectrum measurement, and then you have to do the sample analysis. It is contemporary to the single beam spectrophotometer. Okay. So you have to keep this in mind. So after doing this, after doing the zero balancing, you should not get any intercept over here. Okay, the intercept after you do the zero balancing, the intercept should be 0. Okay, so suppose if there are certain deviations in the concentration over here, and that may lead to the some intercept values, and you have to keep in mind that to avoid this condition, you have to put the constraint of C equals to 0 while you are doing the modeling. So thereafter, whatever the straight line you will be getting, you have to accept that. Now, there is a very good question. One of the in one of my classes, previous classes, one of the student asked, "Sir, do we have to find out the correlation? And correlation should be how much? And if it is high, what would happen? And if it is low, what would happen?" Okay. So herein you have to keep in mind that we are dealing with two types of data. The first is the experimental data, absorption values, and the second is the data which we are getting through the mathematical model. Okay. Now over here, what you see. So you will, how do you say that it is a good fit? We say that it is a good fit if our R square value is equal to 1. If the R square value it is equal to 0, that means there is no correlation between the two sets of data. Okay, so usually R-square value of 0.99 and above, it is assumed to be a very good fit, and the R-square value as it decreases below 0.99, so say it goes down to 0.98 or 0.97, then we say that the quality of the data, it is starting to degrade, and usually we accept any value which is greater than equal to 0.95. Okay, so this means that we are accepting 5% of error. Are you getting my point? So we are accepting 5% of error, and while accommodating that, we need to see that the model which will be creating, it is having a correlation coefficient of R-square value of greater than equal to 0.95. Okay. Another important thing, when you are doing these measurements, it may so happen that the absorption value, it is greater than 0.8. In many machines, you will find that the absorption value you can measure up to 0 to 3 or even 0 to 4. That's very good. But conventionally, what we saw in our lab, if the absorption value is within 0 to 0.8, then we have a very good quality of the data. Okay. This is because when we are talking about the detectors, they are not ideal detectors. Okay, so any detectors, they have some non-linearity, and it has been found that the non-linearity, it increases above 0.8. Okay, so if you see here, I have drawn a concentration versus absorption characteristics. So up to 0.8, you can see that there is a linear relationship, and after that this linear relationship is lost. Now what happens if you get a value of say 1? In that case, you need to dilute the solution. Okay, so whatever the solution you have got, say x mg per ml, now you have to dilute this x mg per ml, say 0.5 x mg per ml, or so. This is just an example. Okay, so here it is, I'm getting a value of 1.2. So that means if I uh, dilute it by 50%, so I should get 0.6. In this range of 0.0 to 0.8, so I can go for the dilution of 50%. So that means 0.5x mg per ml, and then um, we will measure, and if we get whatever the readings we get within this 0 to 0.8 region, we accept that, and then in the calculation you have to include those dilution values. Okay, so this is the thing. Anything you need to ask up till now? Until now, do you have anything to ask? No, sir. You guys don't have any problem? Okay. Now, what is the law which governs with the measurement of this thing, or the calculations of the UV visible spectrophotometry? And that law, it is called Beer's-Lamberts law. Sorry. Beer-Lambert law. Herein, absorption is given by log 10 I0 by I which is equal to epsilon CL. So what is I0? So the incident radiation, it is having an intensity of I0, and the transmitted light, it is having an intensity of I. And epsilon, it is given by molar absorptivity, or in some books you will find molar extinction coefficient. Now coming to the Beers-Lamberts law. In the Beers-Lamberts law, we start with minus of di by dx is directly proportional to Ci. Okay. Now what is that? As sample holder, so we have an incident light I0 and a transmitted light I. Now, if we take this sample holder, suppose now this is the sample holder over here. In actuality, what is happening? In actuality, we can divide this cell into a number of subcells. Okay. And the width of each of this subcell is dx. So when the light is being transmitted or it is passing through the sample holder, then the sample holder having a width of dx, it is absorbing some light or absorbing some photons. Okay, so basically what it is, since it is absorbing, we have given this negative sign, minus of di by dx. Okay, minus of di by dx, because there is a change in the intensity. And what is happening to the change in the intensity? Basically the intensity is decreasing with the increase in the distance dx. Okay, and it is uh, concentration of the solution and the transmitted intensity. Okay, so after this, if we replace this proportional, this thing, and we include a proportionality constant over here, we get di by dx, which is equal to minus of alpha ci. Okay, now we take this I down, so we get di by I, which is equals to minus alpha c dx. Okay, so then we put an integral from I0 to I, and dx means it is the subcell or subpart, sorry, or it is the subcells of the original sample holder. So it is minus of alpha c integral of 0 to b dx. Okay. So it starts with 0 at this point, and at the end of the sample holder we have a length of b. Okay, so that's why it is 0 to b dx. So we then perform the integration and we get natural log of I, and I0 to I, limit is I0 to I, which is equal to minus alpha c x 0 to b. And after solving this, we come to this equation, natural log of I0 by I, which is equal to alpha cb. Okay, now converting this natural log to log base 10, we get 2.303 log 10 I0 by I, which is equal to alpha cb. Now from here we get the value of alpha. Alpha is equal to 2.303 divided by bc log 10 I0 by I. So if we compare it with to the first order kinetics equation K, where we have 2.303 by T log 10 A0 by AT. So in the first order kinetics we have T, and over here we have BC. Okay. Now, if you take this 2.303 over here, we get 1 by B alpha by 2.303 by BC log 10 I0 by I. And if we try to calculate this log 10 I0 by I, we get epsilon BC. Now, what is epsilon? Epsilon is nothing but alpha by 2.303. Okay, here. And now this epsilon, it is regarded as molar absorption coefficient or molar absorptivity. In some books, you will find it as molar extension coefficient. Okay. Now, this factor epsilon BC, it is nothing but your absorbance. So A absorbance, it is given by log 10 I0 by I, which is equal to epsilon BC. This is an important equation which you need to remember. Then coming to the transmittance. So transmittance is nothing but T equals to I by I0. So taking log on both the sides, we get log T equals to log I by I0, or log T equals to minus log of I0 by I. Therefore, we can say log T is equal to minus of A. Okay. So from where this minus came, we just, since it is within the log, we just replaced it and we got this thing. And this is nothing but your A. Okay. So from here we can say T is equal to 10 to the power minus A, which is equal to 10 to the power minus epsilon BC. Okay. So also T is equal to I by I0. So percent and T, it is equal to I by I0 multiplied by 100. So I by I0 is equal to percent transmittance by 100. Now, if we take this value and put it over here in the equation 1, we get A equals to minus of log 10 T, which is equal to A equals to minus of log 10 I by I0. Then A is equal to minus of log 10. This I by I0, we are replacing it with this one, percent T by 100. And after solving this, we get A is equal to 2 minus log 10% transmittance. Now, why it is important over here? It is important over here because when we talk about the percentage, it becomes easier for us to compare two sets of data. Okay. So this is, and also what happens, you have, if you look into the source of your source of your spectrophotometers, as the time progresses, its the quality or its ability to transmit radiation, it will come down to a certain extent. And if there is any variation in the light intensity, the percentage is a very good means. Percentage transmittance, it is a very good means to compare two sets of data. Preferred. So you have to keep these three formulas. This A capital. Okay, let me name it as one. Equation 1. A equals to log 10 I0 by I, which is equal to epsilon BC. Then you have to remember this second one, log 10 T equals to minus of A, and consequently its subsequent equation. And lastly, the third equation, A equals to 2 minus log 10% transmittance. So you can have some numericals based on these equations. Okay. Now I am coming to the last slide of this chapter. Over here, initially, if you remember, I talked about that there are two types of spectrophotometers. One is transmittance. Now herein you can see you are having the lamp, then you have the optical system, then monochromator. So both of these, it forms the optical system. and then you have the sample cuvette, then detector, amplifier, readout. So this kind of system, it is called absorption spectroscopy. This method is called absorption spectroscopy, and the instrument, it is called absorption spectrophotometer. Now, as we will go forward, you will find that the other types of spectrophotometers, they also can be the absorption spectrophotometers. Since we are using a UV visible lamp over here, it is called UV visible spectrophotometer. Over there, if we use another type of radiation source, then it will be say that say for example IR. So then it will be IR absorption spectrophotometer. But the general arrangement of the absorption spectrophotometer, it will be like this one. Okay. And the second one is reflectance spectrophotometer. If you see, you have the sample over here. Now, in your probe, both the light source and the detector, they are on the same side of the sample. Herein, in the absorption spectrophotometer, we have the magnetic radiation source and the detector on the opposite sides of the samples, whereas in the reflectance spectroscopy, it is on the same side. Okay, and since it is on the same side, so it is called the reflectance spectroscopy. And it is something like this. You have this input end from where you have the light source. It goes through the probe, and through the probe the light is being illuminated. And then if you see at the middle, there is a darker region. Through here the light enters into the detector, and that information, it is being transferred to a processor. The processor may be a mobile phone or a computer. Okay. Now you have to remember over here the basic architecture of the absorption spectrophotometer and a reflectance spectrophotometer, because as I told you, as we go on the future further, the more number of spectroscopic methods, only the main arrangement will be the change in the lamp position. And suppose in this what you call the optics, it will also be changed, because some are opaque in some of the optics. If they work in say the visible UV visible region, they may not work in the IR region. So to accommodate that thing, the optic part, like the lens and other monochromators, they may be changed to a certain extent. Otherwise, the overall architecture of the spectrophotometer, it would remain the same. Okay. With this, I conclude the UV visible spectrophotometer chapter.